So that's being said. Now we can take a look at some properties of power series. Some properties of power series. My little rant back there about being an engineer versus a mathematician. Well, I had some extra room on that paper, and this is the next topic. I might as well start on a new page, right? So I'll throw the first one right in here, and that will be, I think we said series multiplication comes next, so I'll put that in there. So let's slide this up here. Hello. Okay. So what does this say? Now this is a huge one, and it's really confusing, but it's really not. So it says the series multiplication theorem. If a of x equals the sum of this power series, right? We sum up all these terms and it gives us this function a of x. And b of x, we sum up all these terms in this power series and that converges on this function within some radius, right? It doesn't go everywhere, but it's just within some radius. And this is where it gets crazy. C sub n equals a0 bn plus a1 bn minus 1 plus b a2 bn minus 2, blah, 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 blah. This becomes the sum of a k times b n minus k from k equals 0 to n. What the heck is this all about? Here's what this is. This whole thing here, I'm going to draw a little arrow. All right, just in case this is freaking you out, this is the world's biggest foil. Right, so what is this? Each term, each individual term in this new series C is like a big foil of all the first, so I'm going to expand this thing, say for 4 or 5 terms, and I'm going to expand this thing, 5 terms. And then C sub n is just the foil of this 5 nomial and this 5 nomial, and it looks like this. All right, do we really care about that? Yeah, mathematicians do. Engineers, not so much. But what we do care about is the result, that the sum, the infinite sum now, not just from 1 to 5 or whatever we did here, the infinite sum of all these individual C sub n's times x sub n, convert x to the nth, converges absolutely, to the product of the functions, right? So I can multiply the resulting functions, and they still converge within the same radius of convergence. Right, so this sum, the first one, the second sum, and this one, I can just multiply the functions, and that would be the same as the function of this multiplied thing. All right, yeah, that one's. So I'll just make a note here. This is analogous to this thing we did, the limit as n approaches. Yeah, oh, nope, that's not what I'm doing. Let's erase that. That's not analogous. That's my next one I'm going to do. Anyway, this is just a big foil, so that's it for now. Let's put the next one in, and this is analogous. This is function power. Right, same deal here. This is the sum from 0 to infinity of a sub n x sub n, this power series, right? Converges absolutely on some radius. Then the sum of the same coefficient times some function of x to the n converges absolutely on any continuous function f, or f(x). So I can take, say if I took the square root of whatever my x is, and then it would still converge on the same radius. And that's analogous to that, the limit of the function is the function of the limit that we talked about. But this is getting long, so I'm not going to write that down. Now we've got 2 more really important properties. I'll write that up here because it's so important it starts a new page again. 2 very important properties All right, number 1. Here it comes. 10.7. This is differentiation. Okay, what does this one say? If C of n blah blah blah, this power series has radius of convergence, some radius, so from -1 to 1 or from 3 to 5, whatever it is, this thing works. The function f has derivatives of all orders inside the interval, and we obtain the derivatives by differentiating the original series term by term. So f of x equals, or this is f prime of x. This didn't turn out very well. That should be a prime in there. I better make note of that. This is f prime, and this is f double prime. Okay, so f prime of x and f double prime. So this is first. I'll do this in blue. So this is the first derivative. And this is the second derivative, because this probably will not print well. Right? So what do we do? It's the power rule, right? Here's n, right? It's to the power. So just put the power out front, and then reduce the power by 1. So move the power out front, n times c sub n x minus a to the n minus 1. Second derivative, take the power, move it out front. So now it's n times n minus 1. Ooh, interesting. Times x minus a to the n minus 2. Okay, now you might ask yourself, and I don't want to do that. Get my pen back. Well, that did not make a good bracket. Where is this going? That's a rhetorical question. I'm not going to answer that. So what's going to happen to n times n minus 1? What does that look like? Let's look at an example where we can kind of put this into use. I know that I've got 1 over 1 minus x equals 1 plus x squared plus x cubed plus x to the 4th plus dot dot dot, and that's when x falls in this range, right? If x falls in this range, the radius of convergence, the interval of convergence, then this series converges to this function. Well, if I take the derivative of that, the derivative of 1 over 1 minus x should equal the derivative of this whole thing, 1 plus x plus dot 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 dot. Okay? That should work out. So if I take the derivative of 1 over 1 minus x, well, what does that equal? It's 1 minus x to the -1, so it goes to -2, so it's negative, but it gets multiplied by this. So this really becomes 1 over 1 minus x squared. Check my differentiation there. And this becomes a 0, this becomes a 1, plus 2x plus 3x squared plus 4x cubed plus dot dot dot. Okay, so I can take the derivative of this side, right, of my function to which it converges, and that equals the derivative just term by term over here. So that's pretty useful. So let's do another example of that now that might be more interesting. Go back over here, and we'll say, let's say I'm just starting with some function. Example, f of x equals, let's say, 1 plus x squared over 2 factorial, right, make them a little interesting, plus x cubed over 3 factorial plus x to the 4th over 4 factorial. You can see where this is going, right? And now if I want to find the derivative of that, f prime of x equals, well, derivative of 1 is 0, so that goes away. So this becomes a 1 plus 2x over 2 factorial plus, let's see, 3x over 3 factorial plus 4x over 4 factorial plus dot, dot, dot. I can clean that up a little bit, and that equals, well, that's still 1. The 2, here, 2 factorial is 2 times 1, so the 2's cancel, so this just becomes an x. Same deal here, the 3's cancel, so I'm just left with, this is x, 3x squared, and this is 4x cubed, right? So this is 3x squared, the 3's cancel, and we're left with x squared over 2 factorial plus the 4's cancel, this is x cubed over 3 factorial plus, we can see how the pattern goes, x to the 4th over 4 factorial. So you can see this is the derivative. Wait a minute. 1 x squared over 2 factorial. What the heck? Well, let's take another derivative. What is going on here? I want f double prime of x equals derivative of 1 is 0, derivative of x is 1, plus x squared, 2x, that just becomes x. 3x over 3 factorial, x squared, 3's cancel, x squared over 2 factorial plus 3x cubed, 4x cubed. The 4's cancel, so that becomes x cubed over 3 factorial, but that didn't do anything. What the heck? F of x equals f prime of x equals f double prime of x. It's the same every time. What the hell? Alright, whatever. Edit that one out. Okay. Okay, so let's do another example. One that maybe isn't quite as obvious. Here's an example, and that is going to be f of x equals, let's make it a really cool one here, -1, nope, I wanted to make that the sum. Fortunately, my eraser is handy. The sum, and I'm going to go from 0 to infinity of -1 to the n, and x to the 2n plus 1 all over 2n plus 1. Right? Well, what will that be? So this is basically the odd ones, right? We start at 0 and we'll just go up by the odd ones, but it's going to alternate signs starting with positive. So this becomes, well, it starts out with x, I think, right? Yeah. But then it goes negative by odd powers, x cubed over 3 plus x to the 5th over 5. All right. Well, let's take the derivative of that one. So f prime of x equals derivative of x is 1. And then this becomes 3x squared over 3. Oh, the 3's cancel conveniently, so that becomes minus x squared. And the next one becomes plus, the 5's cancel again there, so that's a positive x to the 4th, and then a negative x to the 6th, so we can see how this is going, a positive x to the 8th. Alright, so we can see what's going on here. Now this is an alternating geometric. So let's write that down here. This is alternating geometric. And the r is, the common ratio is negative x squared. So really I can say that f prime of x equals 1 over 1 minus a negative x squared. So that's 1 plus x squared. The derivative is 1 over 1 plus x squared. Now, I can't spell right now because my nose is all plugged up, but that sure smells like a trig substitution. And that looks a lot like the original f of x. If I were to integrate this thing, this would come out to be arctangent of x. All right. So I knew that was coming. I knew that was going to happen. So I'm going to ask another rhetorical question. How do you think this button on your calculator works? All right. Now you may think that maybe there's some little elves that live inside your calculator, and then they've got a unit circle, and then when you give them some value, that they kind of spin the wheels and crank the gears on their unit circle and spit out an angle. And I guess I'm required by the state of Wisconsin to say that if you do believe in elves inside your calculator, that's fine. But personally, I think that to get this function, arctangent, really it just takes the sum of a sequence that looks like this. It takes whatever number you stick in there, minus that number cubed over 3, plus that number to the 5th over 5, minus that number to the 7th over 7, etc., etc. So, and it only has to do, your calculator only goes to, 8 or 10 places, maybe 12 places if you have a fancy calculator. So it only has to do this, a certain number of times in order to get a pretty accurate estimate of the arctangent, right? And then, since it's an alternating series, we know exactly what the error is of that estimate of the arctangent. So now we're just getting into the real power of these power series. Calculators can only do things. I'm going to write this down. Calculators can do 2 things. Add and multiply. That's all it can do. And so this allows us, division is really a form of multiplication, and exponents are a form of multiplication. So if we only add and multiply, they don't know what an arctangent is. Your calculator doesn't understand the unit circle. All it can do is this, this series up here, enough times to get to the end of the display. All right, so let's keep going here. That got to be a little philosophical. So I think there's only about 1 page left. And I know this is a long one. Bear with me. We're almost done. Change back to black here. And the final definition I'm going to throw in is, or the theorem, is the term-by-term integration theorem. What does this say? That f of x is the sum of this stuff. Well, just like I can integrate a polynomial term by term, this is really a polynomial. I can integrate this one term by term. And so if I went back to, I'll do it over here just because it makes some room. I know that 1 over 1 minus x, well, that could really come from 1 plus x squared plus x cubed plus x to the 4th plus dot, 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 dot. Well, if I were to integrate this side, well, what is that? That's the natural log of 1 minus x. But there's a negative sign there, so I can make that negative. Equals, I integrate this thing, that becomes x plus x squared over 2 plus minus x cubed over 3 plus x to the 4th over 4 plus dot dot dot. And if I multiply it all the way through by a negative, you get natural log of 1 minus x equals negative of all this stuff. And if I replaced x with negative x, then I would get the natural log of 1 plus x equals, let's see, negative x would I would still be left with an x. Negative x squared would remain positive, but that's going to become negative when I do this, so that becomes negative x squared over 2. And then the cube thing will become negative, but that gets flipped, so it becomes positive x cubed over 3 minus x to the 4th over 4 plus dot dot dot. Once again, if you think that your calculator understands what a natural log really is, it doesn't. What your calculator can do is add and subtract, take a bunch of powers a bunch of times, and says, well, if you want the natural log of this, I can easily find the natural log of 1 plus that. So when you ask your calculator for the natural log of 7, it says, well, I can find the natural log of 6. And that turns out to be 7, and so that does this thing here. So there it is, power series. It's pretty powerful stuff, and I hope this makes sense. I know it got long, but maybe if you watch it in a couple chunks over the weekend, you'll kind of let it absorb. You can lay in your bed at night and say, wow, power series, man, this all comes together here. That's it. Have a good night.